Welcome again to the series of talks on convex optimization, and today we are going to start a very important topic called separation theorem for convex sets. As I had already told you that separation theorem for convex sets are important because optimality itself can be expressed as can be expressed through the separation of two disjoint convex sets. So, this topic is of extreme importance to our study, and observe that with the term separation, the term convex set is highlighted here, because in general for a non-convex case this thing called separation need not work. So, what does one mean by separation? What one means is the following, that if you take two convex sets which are disjoint from each other, could be this one and this one, right. They are convex sets, but they are disjoint from each other in R3. Then in R3 you can pass a plane which separates these two, that is, you basically put a border or a wall between these two. So, this thing lies on one side of the wall and this thing lies on other side of the wall. So, in R2, which is our playground, you see here I have a convex set C1, another convex set C2, and they are disjoint, then I can draw a line separating these two. So, this line, which is an hyperplane in R2, divides, as you know, the whole space into two parts. So, C1 lies in one half space, C2 lies in other half space. That is exactly what is meant by separation. I will mathematically describe this thing. Suppose this hyperplane H is given as set of all x. I am writing in the general sense of Rn, though everything is in R2. Suppose this is what the hyperplane is. Then A of z, where z belongs to C1, is greater than equal to B for all z in C1, and A of y is less than equal to B for all y in C2, which is in the lower half space. So, that is exactly what is the meaning of separation, that the whole set of C1 is contained in the upper half space here, in the whole set of C2 is contained in the lower half space. There cannot be an intermingling, that is, a part of C1 is in the lower half space and part in upper half space, and part in upper half, part of C2 is in upper half space and part in lower half space. Such a thing would never happen, but means you can always draw boundary. But look at this non-convex case. This non-convex case, you can draw out. What I have done is I have taken the interior of the first quadrant and interior of the third quadrant, that is, writing more technically, I have taken interior of R2 plus union interior of minus R2 plus, right. Now, look at the union of the second quadrant with the fourth quadrant. Now, if you look at these two sets, this first one and the second one, they are having empty intersection, but can you draw a line such that the one set, this set is in one side of the line, this set is in the other side of the line. Okay, let us try to draw a line. Whatever line you draw, you cannot put one of these sets into one part and another set of this set into the other part, that is, one in one half space, other in other half space. Whatever be your line, it really does not matter. Whatever be your line, it really does not matter. This thing need not hold for the general non-convex case. Of course, you can say, okay, no, never mind, I can just draw a non-convex set like this, another non-convex set like this, and okay, I can say this. Yeah, of course, there can be instances where this can hold this separation, but it will never hold in general for every pair of disjoint non-convex sets, but for every pair of disjoint convex sets, this thing will always hold, and that is what is our goal. So, we would see, we will now prove that such a thing can be mathematically established or demonstrated. Our first case would be the simplest one. C convex set X a point outside it. So, what I am having here is something like this. A set C and a point X outside it. What we intend to say that this set C and this point X can be strictly separated. So, C and X can be strictly separated. So, what I mean by this? What I mean is the following, that X would lie in one of the strict half spaces and C would lie in one of the strict half spaces, that this line would neither touch C nor X. At the same time, dividing these two into two different segments, that is putting X in one half space and putting C in the other half space, it would never touch either of them. So, it means that if this is written as H, as that A x equal to B, then what I have is the following. Strict separation means the following. So, it should not touch, which means in this case X is in the lower half space, C is in the upper half space. So, A of X is strictly less than B and A of Z is strictly greater than B for all Z in C, and that is what we would like to establish. For any closed set C, the set C need not be bounded, it could be unbounded also, it does not matter, but X has to be point outside C, and that is all. How do I establish this? The establishment of this thing calls in to the fore the notion of a strongly convex function, and so we have to learn something about strongly convex functions, which we had already discussed in the last lecture. We learn something bit more and then go in and talk about this separation procedure. So, just recall strong convexity. So, strong convexity means that there would exist a number rho such that for any x y you give me, I can always write for any lambda between 0 and 1, so this is less than lambda times f of y now. This is what is strong convexity, rho being greater than 0. Now, when x is not equal to y, norm of y minus x whole square is strictly bigger than 0, and this would imply that f of lambda y plus 1 minus lambda x is strictly less than f of lambda y plus 1 minus lambda x plus. So, you have added a positive number to this. So, it gets a strict reduction. So, this is again this shows that for x not equal to y, and lambda in 0 and 1. So, then this whole thing is positive actually. Of course, here I have to write lambda in 0 1. F of lambda y plus 1 minus lambda x is strictly less than lambda f y plus 1 minus lambda f x. So, this means that every strongly convex function is strictly convex. So, again I start with a very simple problem, but it is homework for you. So, if f is a strictly convex function, defined on a convex set C, on a closed convex set C, then if there is a minimum there is a minimum of f over C, then it must be unique. But for the strongly convex case, we have a better result. The result is as follows: strongly convex functions always have a unique minimizer over a closed convex set. Those who have some knowledge of optimization, or those who are experts who are just watching this possibly for fun, or trying to see how a fellow researcher is speaking about the subject, for them of course it is obvious and you know how to do it. It is all about coercivity of the function f. So, but for others I would not ask you to get into the details, especially those from the engineering background. I would just like them to keep this in mind. So, that is why strongly convex functions are so important, because you are always guaranteed a unique minimizer over a closed convex set. There will be a minimizer. It does not say that the set has to be bounded, the set need not be bounded, but still it will give you a unique minimizer, and that is a very rather important result which we separate out. How this result is important for us is what we are going to see. So, we are now going back to this situation of a convex set and a point x outside it. So, how do I am supposed to draw a separating hyperplane which is strictly separating in the sense that we have just defined? In order to do so, we just do the following. Let us drop a perpendicular from x to the set C, and then you know that except this point, say which I call as x bar, there is no other point on this line segment which is lying on C. So, through any such line, right, through any such line, any such point, just take the midpoint of this, draw a line perpendicular to this perpendicular line to x minus x bar, and this could be the separating hyperplane or strictly separating hyperplane. How do we guarantee that if I just drop a perpendicular, there would exist an x bar, it will go and hit, and of course, from this picture it is clear that if you draw a perpendicular on x, it will go and hit a point x bar on the set C, because the set C is closed. So, the boundary of the set is also included in the set. But how can I be mathematically sure that such an x bar would always exist, such an x bar will also be there, and this would lead us to this result. We will just use this result. So, we will now first talk about when there is a point x and a set C, what we are trying to measure by the perpendicular. We are trying to measure the distance between x and the distance between x and the set C. So, what is the meaning of distance of the point x from the set C? So, what you do is with every point in C you calculate the distance of x. Basically, you calculate the length of x on every point y in C, you calculate the length y minus x. So, basically what you do, you calculate for every y in C you do that, and by the distance it is very clear should be the minimum one, that is the distance from the point x. So, you take the infimum of these values when y belongs to the set C. So, how do I guarantee that this would happen? So, finding the distance is same as trying to find the square of the distance, in the sense that I can look now at the problem of minimizing So, any solution of this problem is obvious is a solution of this problem, and I am not going to tell you how to do that. This is so clear that you can just take up a pen and paper and just finish it off in a minute. So, now observe that this one is a strongly convex function. This function is a strongly convex function. So, homework is as follows. Of course, in our general writing y and x, these all are in Rn. So, this set C is in Rn. In our general writing, we will write everything in terms of general spaces, though explanations would be in R2. So, f of x is equal to show that it is strongly convex. Find rho in this case. Now, this set C is a closed convex set, and this is a strongly convex function. So, what we have said that strongly convex function always have a unique minimizer over a closed convex set. So, there must exist some y in C such that, so what would happen is that there would exist a y bar say in C such that y bar minus x whole square is minimum of so the x bar what we are calling here is actually what is the y bar we have just written, same thing. So, I will just draw again for you the picture. Now, this simply means that the distance of x from C is nothing but norm of y bar minus x. So, what I am always guaranteeing that there exists a unique point y bar, because the minimizer is unique. Of course, this y bar is unique, there cannot be more than one. There exists a unique y bar such that at that point norm of y minus x bar, this is the distance of x from C, that is the minima is achieved at y bar and is done uniquely. So, more generally y bar is called the projection. You know, when you have the x y coordinates, so if you have x y, so what you do, if you drop a perpendicular on the x axis, you get the x coordinate, if you drop a perpendicular on the y axis, you get the y coordinate. So, it is the same idea. So, y bar is called the projection of x on the set C. Now, the crux of the matter is as follows. Take this convex set C and take this x. This y bar of course is the nearest point from x, nearest point from x to C. But you see, if I take an x bar here, this another say x dash here, it is the same y bar which is the nearest. This is not the nearest, because then it will not be perpendicular, it will be slanted. If you take another x double dash here, then you see the same y bar is the nearest one. So, a single point y bar could be the nearest point of projection points to many such x bars. So, for any vector on this line, on this line, on this line, or anything in between, the projection is the same point y bar. For example, if you take it on this side, suppose you take some x tilde, then the projection here is y tilde, but y tilde cannot be a projection to this point, say x hat, the y tilde cannot be a projection to x hat, here the projection would be y hat. So, at these rough corners of convex sets, these sort of situations can arise, and this thing actually forms a cone. That is, the set of all x's will actually form a cone, which will be called a normal cone in the future. This will be called the normal cone, but that is not exactly what we need at this moment. We will go ahead and discuss this thing slightly later. We will learn about them slightly later, but what I want to recollect at this point is that at these points, that is at the, for all these x dash, x tilde, x double dash, y bar is the only projection point. Now, you see, if I do not have a convex set, this unique projection business does not work, because for example, if you take the set which is epigraph of y equal to minus mod x. So, you take the epigraph, the set C as the epigraph of minus mod x. So, take any point on the line here, drop a perpendicular, this is the nearest one, drop a perpendicular. Just by symmetry or from simple Euclidean geometry, you can prove that this side is equal to this side, right. Because what would happen is that if this, because this is equal to this, because these are at 45-degree angle. So, this is equal to this. So, this is also equal to this. If this is 45, this is 45, this is 45. So, what does it mean? It means this is equal to this is equal to this, 45, 45, the same angle. So, this is an isosceles triangle, this is an isosceles triangle. So, this is equal to this is equal to this, and so I have this side is equal to this side. Now, once I know this, so this for this point x, this y bar 1 and this y bar 2, two different points, both of them are projection points. But because this is a non-convex function and so the epigraph here as you see is a non-convex set, for a non-convex function a point outside the set can have two different projection points. Such a thing cannot occur just because of the use of the factor use of this idea on strong convexity. Optimization is a great and beautiful subject because these are proved in a very simple and very beautiful manner, but we will not get into all these things. So, now we will start proving what we had just discussed. So, we will go back, draw the picture again. See, so there is a point say x outside, and then I want to describe the hyperplane which will strictly separate the two. Let me mention that what I am going to give you here is a sketch of the proof, not absolutely hand waving, but not extremely rigorous either. So, what we really need to look here is the following, that if you take any point, or maybe I will just make it more, y inside, and this is y bar which is the projection of x on C. If you join y with y bar, this angle is always obtuse. Whatever y you take in this convex set, this will always be true. Now, this proof we are avoiding at the moment because it needs certain calculations which will go on. So, we are just avoiding it, but from the geometry you can really make it clear to yourself that this is exactly what is happening. Now, let us look at something more interesting, is that you see, let me denote by S x minus the projection of C, projection of x on C, that is x minus y bar. Now, this S cannot be equal to 0. So, obviously, x and y bar are not the same point, because x is a point outside C and y bar is a point in C, because y bar is a solution of a constant minimization problem. So, y bar must be feasible and hence y bar is in C. Now, we will employ this obtuse angle business that we just spoke about. In order to do so, what we do here is the following. So, S is this one x minus y bar. Now, take any other y here, y minus y bar, this inner product. So, this is your S, this S vector. This inner product must be negative or non-positive, because the angle is obtuse. You know how to do dot products. So, I can now write S of y minus, what is y bar? Y bar is x minus S. So, you have S y plus S minus x, or S S minus S x plus S y to be less than or equal to 0. So, this can be written as norm square of S minus S x plus Sy. This simply means that S of y is less than or equal to S of x minus norm S square. We take this thing to the other side. Now, observe that norm S is not equal to 0 because S is not equal to 0. So, this is strictly less than S of x. So, this is what we actually have obtained, that okay. Now, you can say okay, I have got a strict separation, take any number which is between S x, which is lying strictly between S x and norm S square, and that will do the job. S x minus norm S square and S x. So, take any real number lying between this real number and this real number strictly in between them, and that will do the job, but we can really figure out an exact one. See, you can write this as following: supremum. So, this is true for every y in C. So, this thing is true for all y in C. So, you can write the supremum over y in C of S y. This is obviously less than equal to this, which is strictly less than this, and hence the whole thing is strictly less than S of x. Now, this is a representation of from this projection business, but how do I really speak about the finding the hyperplane? Okay, let me do that. Let us find an R which I can write as half of S x. So, x is given to me, S I have found. So, I am writing this plus the supremum. Of course, the supremum here has a finite value because it is bounded by S x, as we have seen. Supremum S of y, where y is in C, this is a plus sign. Of course, this R is depending on your choice of S. Of course, because it depends on x is again S is again depending on the x, the choice of the point x. So, you have taken this R. Now, this R is what we really want, that is a hyperplane which we like this, or we can write as L is a set of all x such that S of x is equal to R. Observe that S x minus R, what does it give me? It gives me S x minus half S x minus half supremum y element of C S y. So, this will become half of S x minus supremum of. So, this whole thing obviously you know from this fact that this is strictly bigger than 0. So, you get S of x is strictly bigger than this R. So, this is lying in the x is lying in the upper half space. Similarly, you can show that for all y in C, S of y is strictly less than R. Show this. So, this is my required hyperplane which strictly separates. So, we have mathematically demonstrated this procedure. Now comes a second question. Okay. We have taken the most simplistic scenario of a point and a set. How do I extend this scenario to two convex sets, because we were speaking about two convex sets always, they have been non-empty. Of course, just a point x is itself a convex set, and that it being outside a set immediately tells that these two convex sets are disjoint. Now, let me consider this case now. C1 is convex and compact. That is convex, closed and bounded, and C2 is convex and closed obviously. Beware that in this all the statements of separation theorem, this set C was always closed, though need not be bounded. But this set X, a single point, is obviously closed, bounded and convex. So, it is a compact set. So, I am making the first generalization of this by replacing this X by some compact set. You will see why such a first step generalization to include compactness is useful. What I am trying to say is that if this happens and C1 intersection C2 is empty, that is they are disjoint. So, you have a convex set like this, C which is closed, C1 C2 which is closed, but need not be bounded, and you have another like this C1 which is closed and bounded. What we are trying to say is that then a strict separation is possible. So, the thing is, our conclusion is strict separation is possible. Now, you might ask the question, okay, if I throw out compactness from C1, strict separation, is that possible or not? So, our question is throw out compactness from C1, compactness, and just assume C1 to be closed. Is strict separation holding? The answer is of course negative, otherwise we will not get into all these issues. Let us see why that answer is negative. Take the x axis and y axis. Take this plane, this half space along with this line x axis. Consider this to be C2. For C1, consider the epigraph of the convex function y equal to 1 by x for x greater than 0. Of course, the domain is x greater than 0. So, there is a epigraph of f where f is equal to 1 by x where x strictly greater than 0. Now, you see this 1 by x is asymptotically going towards the x axis, asymptotically going towards 0. That is, as you go further and further towards infinity, more and more towards infinity, this distance between this x axis and this curve keeps on decreasing, but they never touch each other. So, now if I draw any line other than the x axis to separate this APF and C2, then no matter what line I draw, there will be a point where it will go and cut the epigraph of f, because it is asymptotically going towards 0, as a result of which even though these two sets are closed and they are having empty intersection, you cannot have a strict separation. Here the separating line is this x axis, the yellow line. So, that is why compactness is so very important. So, how do you go about trying to prove this fact? So, this would be a partial homework for you, not a complete homework. Now, observe, consider the convex set C1 minus C2. Now, of course, it is convex, you can prove it, I do not need to do that. Now, observe that 0 does not belong to C1 minus C2. Why? If 0 belongs to C1 minus C2, there is a common point between C1 and C2, because then there exists a x in C1 and y in C2 such that 0 is equal to x minus y, and hence x is equal to y. So, both are in x is in. So, these are common elements of C1 and C2, but C1 and C2 is disjoint. So, this cannot happen. Now, you observe here is a convex set and there is a point outside it, and if this set is closed, I can apply what I have learned just now. The question is C1 minus C2 closed? So, this brings us to the following question. So, if C1 and C2 are two convex sets and both are closed, the question is this closed? Is C1 plus C2 closed? This answer is not true in general unless one of them is compact. Here we have assumed C1 is compact, so C1 minus C2 is finally closed, but here C1 plus C2 in general, because minus is nothing, just you can say plus or minus C2. So, C1 plus C2 is not closed unless one of them is compact, because you take again an example of this type where you take a convex set like this, y equal to 1 by x, and this is y equal to minus 1 by x. Look at these two. So, take any 2 points. So, take a point here and take a point here. So, this is my C1 and this is my C2, both are closed and both are disjoint from each other. In fact, you see, of course, disjoint is not needed. I want to construct C1 plus C2. So, I take a point here, I take a point here, I do the vector addition. Okay, let us take this point here. So, I do this vector addition, I get a point here. So, what I am doing is that if I keep on doing for all points here like this sort of combinations, I will basically get this set, this whole half space, but I will not get this line, the red line. So, this red line is not in C1 plus C2. So, but this is a part of the closure of C1 plus C2, closure of the half space. So, as a result C1 plus C2 in this case, this one is not closed. But in our case, because we have assumed C1 to be compact, so C1 minus C2 is closed, and of course, now you can go ahead and apply the result that you already know. So, that application has to be done as an homework. So, finish this thing as an homework. So, strict separation can be done between C1 and C2, C2 when C1 is compact and C2 closed. There is another very important conclusion from this. All this is a study of the supporting hyperplane theorem. So, if you take a convex set of this form, take a point here on the boundary, you can always draw a tangential line through the boundary, so that this hyperplane creates a half space and the whole set C is in one side of the half space. So, here is the convex set, and now here is a point x on the boundary. I can always prove that there is a hyperplane passing through this point x, so that the whole set C is in one half space, it does not have two half spaces. For example, if I take a point inside and if I try to draw a line, I can draw a line, then it will the set C would be covering both the half spaces. But here in this case, where I have just the set C and a point here, and I draw a line here, for example, tangentially in this case as it looks like in the picture, then C is in one half space, it does not come in spill over to this half space. This whole thing, this is called a supporting hyperplane. So, what does it say is that if you give me a closed set, then I can always have a supporting hyperplane. So, what is the idea behind this fact? The idea is as follows, that if you have a closed set, so you know this supporting hyperplane does not mean that it will touch only at one point. For example, here I can have this itself. So, suppose this is a convex set. So, this whole side can be a part of that supporting hyperplane. The idea essentially is as follows. Suppose you have a set C and because you take any point x in the boundary. So, given any point x in the boundary, there is a supporting hyperplane passing through that point. That is exactly what the theorem says. So, what it says that if, because it is in the boundary point, any neighborhood you take, there is a point in C and a point outside C, that is the meaning of a boundary point. And as a result, you can have a sequence of points coming and converging to x. Keeping in view the audience, I would not like to go into the details of the proof, because it would require more sophistication and would really be a proof for mathematics students. So, I am assuming engineers are also viewing this. So, what you can observe that if you keep on drawing this sort of balls around x, there will be a point inside x and there will be a point outside x. So, those x's, those point sequences, if you think of it as something you are hopping one after another, you can hop on these points and come on to x. For each of these point x is actually a point outside the set C in C complement, and from there you can have strictly, for each of them you can have a strictly separating hyperplane. And finally, you can come in like this and come and touch the boundary at x, and that would give you. So, basically what would happen is that would generate a sequence of planes which can come and touch in x, and that would give you the separating hyperplane, or the not the separating hyperplane, the supporting hyperplane to C at x. So, with this very basic ideas about separation, we close our discussion and go into more of the optimization issues in the next class.